T, force of carrot, times that distance. Let's call that distance the full length, capital L. Okay, capital L. Great. And again, they get sine of sine of 90 degrees is 1. Great. And so this whole thing equals I of my jaw about the left, my little pivot point at the hinge, right, times alpha. Oh, yeah, but we're doing a static problem. We want to know how much force is being exerted while I'm in static equilibrium. So this is 0. It's 0 because alpha is 0, not because I is 0. So just so that's 0. Great. So this is a very simple equation. It just says it's the same equation as we got over here. It's just that we're talking about it now with the fulcrum. This is a situation where you've got two things like this, as opposed to something that's like this, right? But it's the same idea. The further you are from that pivot point, the bigger the torque is for the same force, right? So that means that. So from this, is the force exerted by the muscle bigger or smaller than the force exerted by the carrot? I heard one person say it. The force of muscle bigger or smaller than the force exerted by the carrot? It's bigger. That's right. So the way our bodies are built, we exert bigger forces from our muscles in order to achieve some force at the extremes of our extremities, or whatever, at the end of our teeth or at our fingers or whatever. It's kind of surprising in a way because we're pulling harder than we would have had to, maybe. But there's real advantages to putting muscles close to the joints. One is you can put your jacket on, right? We have muscles that are out here, and muscles in our fingers and stuff. Awful, right? It's better to have the muscles away from the places where you're going to use the action of the muscles, and they make them close to joints. You have to lift them less often. They're closer to your trunk, closer to your body, and it also allows you to move quickly. Like if you want to throw a ball, how do you do that? Well, your muscles only like if you want to throw a ball, or a chalk, or whatever. I want to throw it so that I'm going over some distance that's pretty long, like a couple meters. My muscles, no muscle in my body can contract over a couple meters. It can only contract over shorter distances. So if you want to translate a small contraction of a muscle into a big motion of your limbs, how do you do it? Well, you do it by having those muscles acting very close to a joint, and that way a small, a little displacement of this place next to my shoulder joint, right, allows for a big displacement of my hands. It's another reason, right? So it makes sense. And for your, the thing that's interesting about your mouth, you want to shoot things with a large force on a carrot. Well, you're never going to exert as big a force on the carrot as the master muscle itself is exerting on the jaw. But you can make it as big as possible by making L as small as possible. If you want to make this equation true, which is just static equilibrium, just Newton's second law with alpha equals 0. Excuse me, Newton's second law for rotation with alpha equals 0. How do you make F sub c as big as it can be? When you can work out and make your master muscle bigger or stronger. But once it has some maximum strength right now, whatever it is, and it's fixed, it's connected to your jaw in a fixed location. You can't move that around. Maybe there's some creatures that can, but humans can't, right? The only thing you can do is move the carrot closer into the hinge, right? Get it closer into. Let's see. And just to be clear, this distance L, is from. I defined it correctly. It's from the hinge. So you make this as small as possible. And how you do it? You do it by moving this closer to the back of your mouth, and that gives you a bigger force. And that's why you put the molars in the back. And then for finer stuff, when you're trying to chop something out, it also makes sense. If you're trying to bite something off of a bigger piece of stuff, you want to have thinner teeth in the front. That makes sense too. So there's a lot of reasons why your teeth are the way they are. But a good reason that we didn't have some molars in the front is that if you want to exert a lot of force, you want to do it in the back of your mouth, and that's why. So good. So that's the two main things I wanted to get from this are that the intuition you've got for this problem with the teeter-totter with the big boulder on one side and the little guy on the other, and where you're going to put the fulcrum to balance that out. That intuition works for other situations too, including when the hinge is at the side, like the situation with the jaw. And also, you have a problem on this week's homework, for example, right? And students come in after I asked about it. The thing that students often forget, just like forgetting about that hinge force over here, like forgetting there's an upward force, downward force from the skull onto the jaw where the hinge is, right? In this problem, what are the forces? Well, it's the downward force of the boulder acting on the beam, the downward force of the man acting on the beam, but there's another force in the problem, right? It's this fulcrum acting with an upward force on this beam. That's the most common mistake with these sort of problems, just to leave that out. So don't forget to think about all the forces in the problem. All right, so that's our discussion of masseter muscle. We do the same thing now for bicep. People were asking about biceps a minute ago. Let's see if I actually managed to get this up here. I'm loath to take it down. Here we go. There we go. Yes. When I teach this class in the other semester, in the fall semester, this always falls around Halloween, and it's great to pull out that skull. But this time of year, it's not seasonal now. I'm sorry. So anyway, oh my goodness, I'm gonna get hurt. It's time to get a new sleeper sofa, and you get clocks taken out of your car. All right, here we go. Yeah. So here's the idea. If you want to lift up some piece of mass, once again, this is your bicep muscle, right? It connects close to the joint, really close, like a factor of 10 closer than where the mass goes out here where your hand is, right? And if you want to, I'll turn this thing around. I'm dropping my foot. Yeah. Ooh, don't rush on the table. Come on. Oh, he's cheating. All right, good. Anyways, you see the idea. It's the same picture as we got up there, except instead of a jaw, I've just got, I guess there's two bones in this part of your body, but we'll just pretend it's one. You have one bone along here. Actually, there's only one that's connected to your bicep. That's fair. So you have your bicep pulling on one of these bones. There's a very short distance here, a bigger distance here. And where are all the forces in the problem? Well, once again, there's a downward force to the weight over here. There's an upward force to your bicep right here. There's also downward force to the gravity on this bone, but once again, unless you've got some pretty meaty arms, right? I mean, the amount of gravity acting, the force of gravity acting in your arm is going to be negligible. Well, I shouldn't say that. I guess it depends on whether you're holding weight or not. Obviously, in terms of how much weight, in terms of how much it matters where the weight is, right? The further it is from this joint, the more you have to exert force over here to support the same amount of weight, right? For the same reason as we have before with the carrot. So if I move this in, and I use this hinge right here as my pivot point, right? The closer in that weight gets, the less torque it's exerting about this pivot point, and the less force I have to exert with my bicep to hold it, right? But so once again, if you want to hold a lot of weight, it's actually less force on your bicep to put it in closer. But there's other reasons not to do that, like you don't have any fingers back here. Anyway, at least you probably don't. What else are you thinking? Oh yes, and the final force we'll forget, the force of the hinge. So which way is the force of this bone acting on this bone? Up or down? Force from this guy acting on this guy. Up or down? People are saying up. A few downs. Who thinks it's up? No one's voting. Two votes. Who's down? Lots of downs. And I agree with the downs. There has to be a downward force here for the same reason that there's a downward force on the jaw at the hinge. Boy, that's a strange drawing I sit back on. I think I need to go down. Anyway, downward force right here. And you know that's true because there's an upward force here, downward force here, downward force over here, and another one here that's small. The result is that if I want static equilibrium, if I had upward force here and here and downward here, it would do this. Can't be. Got to be a downward force right there. Good. All right. Super. I'll leave them up. Great. So that's a whole bunch of stuff about sort of two canonical examples of anatomy and how it relates to torques and forces. So one more thing to say about static equilibrium has to do with stability. So I showed you that. So I started off talking about static equilibrium with the example of that funny spool. Remember that? This is one of my favorite toys to write about for you guys. Let's see. Am I up there? Oh yeah, there we are. Can we lower a little bit so you can see what this thing is? No. All right. Here, I'll hold it up. You see? Huh? Oh, it's down here. Is that good? All right. Do you see what it is? It's a little horsey. And there's a rod here with a. This thing's crazy because isn't that disturbing? It doesn't fall down. this keeps me up thinking about this. So what's going on here, right, is this is an example of stability, right? It doesn't seem like it should be stable, but it's just an optical illusion a little bit, right? Because we're the center of mass of this thing. There's a piece of lead down here, and there's a stick holding it. So this piece right here by itself, right, its center of mass is below the platform. So this thing is really just acting like a pendulum. It doesn't look like it, right? It's sort of cleverly designed thing, so it looks wrong. But that's what it's doing. There's a center of mass on here, and it's going back and forth. That's just an example of a stable situation, right? Because pendula in general are stable because you've got some mass, and if you move it away from the center, right, there's a force that wants to restore it to the equilibrium position, right? So you know this. You've seen lots of examples of this. Springs, right, with masses on the end, right? If you lift it up a little bit, he wants to go back down to the, to the equilibrium position. If this is delta x equals 0, right, and this is our x-axis, and say, this is where he wants to sit. This is an example of restorative force. This thing has a restorative force. In fact, it's a restorative torque, if you like. It's being torqued back to some equilibrium position. Here's another example of a static equilibrium. So all this is a beaker that's got a sphere at the bottom, and inside the sphere there's some lead at the very bottom of this thing, and it's stable. It likes to stand up. I wish all my beakers behaved this way, but they don't. So you have to be careful in the lab. But why does that work? So can we figure this out? If you draw a picture of what's happening and say, oh yeah, this thing is just a spherical beaker at the bottom. Right, so some beaker, and it's got some lead in the bottom, like this. Well, where's the center of mass of that lead? Well, when I ask that, let's make a 3D diagram for this guy. So here's the thing. Where are the forces acting on it? Well, there's a normal force acting up where it touches the ground. Right, so there's a normal force right here. That's normal. But there's also a downward force to the gravity acting on the lead. I mean, the glass is very light, very low density, and very thin compared to this big piece of lead in the bottom, right? So the result is that right here in the center of mass of this lead, there's a downward force due to gravity, right? And when it's sitting like this, it's stable because the downward force is exactly lined up with the upward force. There's no torque. I drew them offset a little bit so you can see the drawing, but if I do it really carefully, they'd be exactly lined up. So not only are they the same magnitude, I didn't draw them the same thing. I did. Not only are they the same magnitude, which means that Newton's second law says that there's no acceleration to the center of mass upward or downward, which is good, right? And there's no horizontal forces, so Newton's second law says there's no acceleration to the left or right, which is good. But what about torque? Well, if they're lined up, then for any pivot point I choose, it turns out that there's no net torque, right? Suppose I choose the center of mass as the pivot point. Well, in that case, what's the torque due to gravity? What about that pivot point? 0. What about the torque due to the normal force if I use this pivot point to center of mass? It's also 0. For a different reason a little bit. The force is actually acting not at the same location as the pivot point now, but it's pointing right at, so the angle is 180 degrees, or is it 180 or is it 0? Either way, it's 0, right? But let's see what happens when we turn the thing to the side and see if it's stable. Because there's a lot of cases, like suppose I have this chalk, right? It's also true if I balance the chalk on the tip. It's also got the same situation, right? The downward force of gravity is exactly lined up with the normal force, but no matter how carefully I try to line this thing up, it's going to fall over, right? Why is that? This is an example of unstable equilibrium. In fact, I wouldn't call it equilibrium. I'd say there's a point that's an unstable point. It can go either way. I guess it's equilibrium. Yeah, it's unstable equilibrium. And this is an example of stable equilibrium. So why is this stable? It's stable because if I move this thing one way, let's draw a picture of what that looks like. Suppose I move it over like this, right? Well, this lead is not molten lead. It's right stuck to the bottom. I drew it bigger here than there. Sorry about that. But anyway, the center of mass now is over here. So here's the downward force due to gravity acting on the. Sorry, I didn't draw that perfectly horizontal. And where's the normal force acting? Well, it's a perfect circle. So if I drew it right, so it's actually pointing up toward the center of the circle. So the normal force now is doing this. Does everyone see that? It's like that. Got too many lines on this drawing. So I got an upward force, normal force like that, and I have a downward force of gravity, and they're offset. Right? It's not that I didn't draw it. Well, I didn't draw it carefully, but even if I had drawn it perfectly, they would still be offset. Right? As a result, there is a net torque on this object. If I do if I rotate it that way, the torque wants to right it. It wants to bring it back up that way. See that? Because it's pushing down right here and up right there. So if I ask, what's the torque about? Let's take the center of mass as our pivot point. What's the torque about that center of mass? Well, there's no torque due to the force of gravity. But look, there's a positive sense of rotation type torque due to the normal force, right? It wants to rotate it that way. Does everyone see that? And you might say, well, wait a minute, but that's because you chose that as a pivot point. What if you choose this as a pivot point? So let's choose the point of contact there as a pivot point. Which is actually valid while it's rolling around, even if it's not a static problem, right? Because that's the stationary point of the object. So we can use Newton's second law for rotations with this point as a pivot point. If I use that as a pivot point now, what's going on with the torque? Well, once again, I get a positive torque, right? I better get the same answer for the net torque. And we do, because right here, this guy is giving me no torque, but this guy is giving me a non-zero torque. And it's this way, right? The force of gravity is down, and it's acting to the right of the pivot point. In fact, what's the radial arm? If that's my pivot point right there, by radial arm, I mean what's the perpendicular distance from the force in question from the pivot point? It's that distance right there. So if I want to calculate the torque, if I do, the problem description told me what the separation is, how far apart are these things? I just multiply that, whatever it is, 3 centimeters or 1 second, whatever it is, times the force here, Fg times mg, right? So now it's telling me what the torque is at that moment in time, and therefore I know what the angular acceleration is. Now in this problem, the angular acceleration is changing with time, right? In fact, it changes sign. Like right here, it's rotating now, and over here, it's rotating. I should be careful how I say it. Right here, the angular acceleration is that way. It's being accelerated up like that. And when it's on this side, it's being accelerated up that way. In fact, it's being accelerated this way, even when it's moving that way. For the same reason that gravity is accelerating this guy down, even when he's moving up or moving down. It doesn't matter which way he's moving. It's that once he's over here, the torque is in this direction, and when he's over here, the torque is that way. So it's a restorative force. So that's an example of stable equilibrium. And you can see why it happens when you draw a careful diagram and think through your torques, right? Another example of equilibrium to talk about isn't this sort of dynamical stuff. So I don't know if you have a problem about that on this homework or not. Next week probably you will. Yeah, you get this calculator stuff next week. That's right. So here's an example. So I know we used to go to Pisa and actually look at the Leaning Tower of the budget cut. So here's my Leaning Tower of Pisa. I'm sorry, but it was different when I was a student. So here's the tower, right? It's leaning over, but it's not toppling. It's fine. But if I put the little top on it, it's not stable anymore. So why should that be? I know you can hear somebody's really alarmed about this. It's not the real tower. So why is it falling over when I do that? Let's draw a picture of it. If I draw a picture of what that thing looks like without the top on, it's kind of like this, right? And the center of mass is right here. Here's the center of mass of this thing. So there's the center of mass. Well, the crucial aspect of this picture that makes all the difference, if I do this right, is that this thing is, if I make a vertical line, it's to the left of the rightmost part of the base of the structure. Does everyone see that? So why doesn't this thing fall over? Well, it doesn't fall over because if I put a normal force down here, it's able to balance out the downward force due to gravity acting on the center of mass. So here's, there's some downward force of gravity right here, right? So that's mg, right? And there's upward forces, there's an upward normal force. But the thing is, we have a structure with an extended base like this, and when we get into static equilibrium, we have to worry about the fact that things are extended. I know we have a problem before where I can ignore the thickness of the beam, but this is a problem where it really matters exactly what the base is doing. what matters here is that we're allowed to put the normal force wherever we want it. In fact, we can put it in a couple different places. After all, if there's a building sitting here, right, there's probably upward forces acting in many different locations. So where should we put them so that this thing has zero torque? Well, there better be at least some upward force to the right of this. Well, how do I say that? Let me say it this way. We have all the upward force acting right here, and that would give a situation with no torque, right? If the normal force is acting right here straight up. Otherwise, if we put some force over here, well, we better have force over here such that the torque balances out. You have all the torques and the problem balance out. But you can't do that once I put the top on, because when I put the top on, what happens? Right, so I put the top on this guy. So now the center of mass comes up here somewhere, and let's say that it's just to the right. I didn't draw this perfectly, but just to the right of the rightmost part of the base. So if that's our situation, if we have a downward force due to gravity, and now we can put upward forces anywhere down here we want, but it doesn't help us, right? No matter how far I go to the right with my upward force, it's not going to be far enough to line up with the force of gravity. Does everyone see that? So that means that the best I can do is this. Some normal force, right? Upward. But that's resulting in some torque. Is it positive or negative torque given this convention? Is that a positive or negative torque on that Tower of Pisa? Positive. It's trying to rotate it. And in fact, that's what would happen. It would topple over. This is not a static equilibrium situation. It's not any kind of equilibrium situation. You have non-zero torque in the problem. So there are some problems you encounter in this class, I think, or you may or may not. I don't know if not. These lines are a little weighty because I drew them at the end of the lecture on my arm side. It should be a vertical straight line. A vertical straight line here, vertical straight line here. It's just they're offset. They're offset because it's too far over. In other words, if you draw a picture of a standing, well, here, if I put a book on a shelf. Here's some bookshelf, or countertop. I can put a book over here. That's no problem. Lay it over there. I can also put a little bit of the edge, but I can't put it more than halfway. Assuming the book has, I can just barely do that where the center of mass is just at the edge. If I do that, the only way I can do that is if all the normal force in the counteract in the book is all concentrated right at the end. And in fact, that's sort of true. Well, it's exactly true. As you push the book over and over, more and more toward the edge, more and more of the force is the upward normal force from the table onto the book is concentrated at this point. It has to be. Otherwise, if all the normal force were acting over here, this thing would be spinning like that. Because there's a downward force of gravity acting right there. Too small for this piece of chalk to draw. But and you can't push any further. You have it hanging off the center of mass is off the edge of the cliff here. There's nothing you can do, right? All the normal force is going to be pointing to pointed to the left of the downward force due to gravity. So you'll result in a positive angular acceleration. There's no way around it because you have a net torque that's non-zero, right? There's a lot of interesting things happening when you stack books. So this is as far over as I can push this book. What about the next book? How do you think about that? You can put that book on top and push it over a little ways, but you can't push it halfway over, but you can push it a little ways. How far can you do it? And the way to solve that is to think about where the center of mass is of everything above this edge, and whether that's, how do I say that? Think it's the right way? Well, maybe I should let you think about it. But it's essentially what it comes down to is thinking about the center of mass of different collections of objects, because you have a stack of books. You think, okay, well, which collection is the one that matters? I'll let you think about it. I don't know if it's a homework problem or not. I don't know if it's in it. But anyway, but this is another aspect of equilibrium. It's trying to figure out where can you put the normal forces so that you can make all the torques, make the net torque go to zero in a problem. And then there's this other aspect of equilibrium, which is the restoring force. Will something be stable or not? Physicists spend a lot of time worrying and wondering about whether things are stable. So what they do is they'll say, well, if I perturb the system in this one way, do I result in a torque that restores the system back to where it was, or is it going to push it away from where it was? And that's a really important question because it says whether or not your device is going to explode or whether it's going to do what you want and correct itself without, So that's, when you build a nuclear reactor, it really matters. Do you design it so that it's stable or so it's not? Right? These are important questions. Anyway, so we'll get into fluids next time, and I will see you then. Next time, next week is spring break. Have a nice break.